Okay, so here's what we were talking about last time. We were talking about parameterizations of lines in R3. I come to think of it, I guess this would work in R2 as well, but we're going to think of it in R3 just because we can. So if you have a line like that, the idea is that if you know a point on the line, and if you know a vector parallel to the line, then you can easily describe points that are, in general, other points that are on the line. These points will have the feature that they will, well, there's different ways to say it. On the one hand, you could say this difference is parallel to the line, and then we observe that that means that that difference is parallel to the direction vector v, which means it's a scalar multiple of v, blah, 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 and we ended up with this, what we call parameterization of the line, which is just to observe that the line is all vectors or all points, however you want to say it, of the form x0 plus tv. Right? We talked about how this is not a point tester. This is a point generator. So it functions, sort of oppositely from the way an equation tends to function. An equation doesn't generate points, it tests points. This is the opposite. Okay. All right, we did an example. I want to talk about, suppose we have a parametric line, for example, this one. And that's the parametric line. Right? So x is x0 plus t times v. Right? It's just I've written the parametric equations, they call them, sort of one equation at a time instead of as a vector equation. So that's a parameterization of the line. And suppose I want to turn this into a test, right? It's nice to have a point generator sometimes, but sometimes you need to test a point. And turns out there's an easy way to do this, and the argument goes as follows. If a certain point x is on this line, then that point x can be generated by some value of t. Okay, if this point x can be generated by some value of t, what that means is there is a single value t, that t in these equations here, there is a single value that I can plug in that will correctly generate the correct x coordinate, the correct y coordinate, and the correct z coordinate. A single value of t that will do all of those things. Okay. Well, wait a second, though. That t, on the one hand, that t has to equal to this. You look at that first equation. That first equation says x equals x0 plus ta. Solve for t. T has to be x minus x0 over a. It just does, right? But likewise, according to this second equation, t has to equal to that thing. According to the third equation, t has to equal to that thing. So let's repeat now what we've just agreed. I need there to be a single value of t that satisfies these first three equations. That means I need a single value of t that is simultaneously equal to all three of these things. How is it possible that there could be a single number that's equal to all three of these expressions? And there is, of course, exactly one way that it is possible for a single number to equal to all three of these things, and that is if they are all equal to each other. Right? So this is the test. These are what we call the symmetric equations. Let's see, where did I write that down? Here we go. These are called the symmetric equations for that line. If these equations are satisfied, then this is that shared value that all three of these things are equal to. That is the t that generates the point x, y, z in question. So, said differently, a point can be generated by these parametric equations if it satisfies these symmetric equations. That's kind of a neat trick, and of course you can take the algebra the other direction if somebody gives you the symmetric equations and they say, well, what's the parameterization? By the way, that is going to come up. There's at least one homework exercise on that. But given these symmetric equations, how do you find the corresponding parameterization? Well, just realize these things are all equal to t, and then solve for x, y, and z. And that gives you your parameterization. Okay, all right, so it's a neat little bit of algebra example I'm going to let y'all read. I do want to point out that these symmetric equations, let's see, let me come back up to them again. These symmetric equations are kind of two equations, right? So 1 and 2. It's also, from a certain point of view, if you think about it a certain way, it's kind of three equations because I need these two things to equal, I need those two things to equal, and I need those two things to equal. And the fact that the first two imply the third, yeah, okay, sure, but nevertheless, here are three equations that are implied by the symmetric equations. So what I'd like to do is talk about these equations individually. Like, so for example, what does this equation here mean geometrically? We know that the trio, we know the whole symmetric equations all together describes the line. What does just one of these equations describe? And it turns out there's a great answer to this question. It's actually I don't know. Anyway, if you just look at it from just the right point of view, it ends up being almost a freebie. First observation I'll make about that equation: it's the equation of a plane. I mean, you multiply the a and the b and move some things around. That's something times x plus something times y plus 0 times z. Right? There's no z's in that equation, but nevertheless, something times z equals something. That's the equation of a plane. Right? Is everybody happy with that? Equation of a plane. Here's the next observation that I'll make. That plane contains the original line. Now, how do I know this plane contains the original line? Well, let's think through what would it mean for a plane to contain a line. It means that if you give me a point in the line, that point must also be in the plane. Now, how do I know that's true? How do I know that every point on the line is on the plane? Well, any point that's on the line satisfies both of these equations. Therefore, among other things, it satisfies this equation. So if it's on the line, it's definitely on the plane. Right? So we made a lot of progress. So this equation here, this one equation, you pick apart one of the equations in the symmetric equations. It's the equation of a plane containing the line. That's pretty cool. There's a last observation I want to make. So there's of course lots of different planes that contain the line. If you draw a line, right? There's lots of different planes. I'm going to just do that in a different color. There's lots of different planes that contain that line. Right? You can imagine all sort of rotating all around. So of these sort of infinitely many planes that contain that line, which one is this one? And key observation I'll make is that there's no z's in this equation. That means that if you have a point that's on this plane, change the z coordinate. I don't care. Change the z-coordinate however you want. If you start with a point on this plane, you can do anything you want with the z-coordinate. The result will still be a point on this plane. So I claim that to just think geometrically. That means that as you change the z-coordinate, right, that doesn't affect whether a point is or is not on the plane. That means this plane is parallel to the z-axis. Or if you don't like that argument, when you write this out, you've got something times x plus something times y plus 0 times z equals something. That means that our normal vector, which has coordinates that are these numbers, our normal vector is I'm not sure, I'm not sure, 0. And that means that we have a horizontal normal vector. If you have a horizontal normal vector, that means you have a vertical plane. That means it's parallel to the z-axis. Right? So take your preferred of those two arguments, whichever one you like better. Punchline is this plane is parallel to the z-axis. So, of course, there is only one plane that contains this line that is parallel to the z-axis. This is what I like to call the shadow. Right? This is the vertical shadow, the z-axis shadow plane of the line L. So that's the geometric interpretation of that one of the three symmetric equations. Now I'm going to leave it as an exercise for you guys to go through the analogous arguments and try to decide, for example, what is this? Right? What can we say about that equation? Well, that equation is a plane. It contains the line, and think through the rest of the details. And the punchline is going to be that plane is the plane containing L that is parallel to the y-axis. So I want you to think through those details on your own. It's very analogous to the argument we just made. Ditto for the third one. Okay. All right. So if you want to, then you can think of the symmetric equations. I mean, on the one hand, this is a point tester for a given parametric line, and that's kind of nice. But you can also think of this as viewing the parametric line as being the intersection of these three shadow planes, namely the shadow of the plane parallel to the three coordinate axes. So, kind of neat. Okay, moving along. I'm going to talk a little bit about coordinate systems. I'm going to be really quick with this. We're going to do more with coordinate systems later on, but we kind of need to get this said and just make sure everyone's been exposed to these ideas so that we can use them in powerful ways later on. Right now, this is just covering a little bit of groundwork. So here again, we have this picture. We drew this on the very first day of class of what it means to talk about a rectangular coordinate system. And so here's our x, y, z axes, and if we talk about a point, right, then that defines these x, y, and z coordinates, and so you could say that I can describe that purple point P by its yellow coordinates x, y, z. Okay, and rectangular because look at the box; it's a rectangular box. Motivation's clear. Okay, all right. So here's a different coordinate system. I think a lot of y'all have probably seen this before. This is called the polar coordinate system. And if you want to describe, let's see here, I'm going to zoom back out. If you want to describe a point in the xy plane, which you could, I suppose, describe by saying, well, it has rectangular coordinates x and y, or x comma y, suit yourself. Different way to describe that point is to say, well, I could get to that point by thinking of this as the 0 direction and then kind of turning by a certain angle. If I turn by that angle theta to define that direction, and then if I go, this far in that direction, then look, sure enough, that gets me to that point. So if you give me a theta and an r, I know what point you're talking about. Yeah.
It kind of reminds me of one of the homework problems about the coordinate system and like latitude and longitude to find
let's see, was that the New York and Moscow problem? Yeah. That's right. Well, so we're going to get to that. Yeah, that's right. It's a zinger. Yeah. So in a few minutes, I will show you something that, in fact, directly addresses that problem. Yeah. Totally. Yeah. Which I knew as I was writing the problem, by the way.
You knew that it was.
Yeah, so I wanted students to. I don't know. This is not sadism, but I do like students to struggle with a. Yeah, I'm quite sure. Yeah, to struggle with a problem, just to a certain extent, so that when you see the powerful tool that makes life easier, you can fully appreciate it. Anyway, so that was one exercise, just a little bit of struggle, And anyway, we'll talk about that again in a couple minutes. Okay, so there's an oops in the book here. This does need to be the next edition of the book. This will totally be fixed. But I did call this r a distance. That's not really quite right. Distances have to be positive. right? Coordinates don't have to be. R does not have to be positive. R just represents a coordinate in the direction described by whatever theta is. So, given an angle theta describing that direction. Let's see, I'll do this with a pencil. Maybe this is where R equals 3. This is where R equals 2. That's where R equals 1. That's where R is equal to 0. And it can totally just keep going. Right? Here's where R is equal to -1. Right? Negative values of R are allowed. Now you could argue that they're a little bit weird. Why would anyone want to do that? Why wouldn't you just describe that point by using that angle, thus describing that direction, and then just let R equals 1. Now, arguably that makes much more sense, but no, I'm just pointing out, I'm not saying you should, I'm saying you can. Okay. All right, so heads up about that. Okay, so there's a couple awkward things about this is called the polar coordinate system. There are a couple of awkward things with the rectangular system. We have an x-axis and we have a y-axis. With polar coordinates, there aren't really. There is no theta axis exactly, right? So it's a little unfamiliar in that sense. So heads up. Here's another awkward thing. A given point in the plane has unique rectangular coordinates, but a given point in the plane does not have unique polar coordinates, right? So we just talked for example, about, let me use this point right here. I could use that value of theta and that value of r, right? But I could also use that value of theta and then a correspondingly negative value of r, right? I could also, same point, use that value of theta. Nah, come on, why would anyone do that? How weird, right? What's the motivation to do that? Reasonable question. Turns out it does come up here and there. But nevertheless, the point is you can, say, turn around counterclockwise by, 7 pi over 3. And then in that direction go a certain distance. Right? So points do not have unique polar coordinates. And that's a little awkward and uncomfortable. So, heads up. Here's another awkwardness. Just a notation. So, let's suppose you write down, 1 comma pi. What is that? What does 1 comma pi mean? Well, very often people would look at that and say, well, come on, that looks like an r and a theta, so this must be the point where r is equal to 1 and theta is equal to pi. And that would be a reasonable guess, and you could speculate on how often you might be right on that assumption when you're talking to a human being, right, who came up with 1 comma pi. That said, it is perfectly plausible that the point where x equals 1 and y equals pi might need reference at some point. So, if you just say 1 comma pi, it's in fact unclear what you mean, right? So, just be aware, right, of this potential for confusion. If you think there's any possibility that your reader, namely your grader, right, or someone that you're talking to might be confused to what you mean, make sure to be unambiguous. Put an extra word or two in there, polar coordinates or something like that. Here in the book, I've made up an idea that I doubt will ever catch on. But a little subscript. You got a point. If the rectangular coordinates are x comma y, put a little subscript after x comma y. Subscript of r indicating r for rectangular. Right? And likewise, a little p subscript if you're describing the polar coordinates, r comma theta. Removes possible misinterpretations. Okay. There's another oops in here, and my apologies. I think a lot of y'all have probably seen this before. R equals square root of x squared plus y squared. Show of hands, how many people have seen that in previous polar coordinates? Okay, this is not correct. I wrote it down because I, too, had seen this in a class that I took at some point. But it's really not true. Per an earlier comment that I made, griping about...
Oh, it's the...
Yeah.
Yeah, absolutely.
That's right. Well, so that symbol means positive, right? So if you insist that r equals this square root, you're insisting that r must be positive, which it need not be, right? So really, the best thing you can say here, there's this temptation to solve for stuff. You got to have it down to the thing I want equals, right? But you can't always do this. So really all you can say is r squared is x squared plus y squared. Or yeah, if you want to say absolute value of r equals square root of x squared plus y squared. Sure, knock yourself out, right? I prefer to just leave it as r squared is x squared plus y squared. And then I leave it to the user to apply this appropriately as needed. Right? So anyway, that will be fixed in the next edition of the book. But heads up. Note, I did not step on that landmine for this. Right? There's a temptation to say theta is arctan of y over x. But it isn't, because arctan means a certain set of values, a certain set of angles that are the values of the arctan function. Right? Theta need not be necessarily those values. But tan theta is y over x. Okay. All right, so anyway, heads up about that. Okay, cylindrical coordinates is a lot like polar coordinates. It is critically different in an important way, though, and that is cylindrical coordinates is a coordinate system in R3. Some people will call this polar coordinates in R3. And I don't know. I guess it's okay. It's more syllables than cylindrical coordinates. Right? But for the way you think about it, if it's helpful to you to think of this, hey, it's just like polar coordinates, just in R3, that's totally fine, because it really is. I mean, so notice how this coordinate system works. If you want to describe this point, what you do is you look at its projection down into the xy plane, and you use good old, plain old polar coordinates to describe that projection down there. And then to acknowledge that this is a point in 3 space, we have to identify with the z-coordinate as well. It's the exact same z-coordinate from rectangular coordinates. So you can think of it as polar coordinates in R3. Totally fine. Okay. By the way, I guess I forgot to acknowledge this. This is right here in the notes, but I should have said it. In polar coordinates and rectangular coordinates, here's the relationship between the variables. X is r cosine theta, y is r sine theta. Again, I think y'all have probably seen that before. If you haven't, easy to observe. It's a little bit of trig. A little bit of trig on this diagram right here, which I've got too big. A little bit of trig there that x is r cosine theta. Okay. Ditto and cylindrical coordinates. Now, there's a third coordinate system we're going to make a lot of use of. This is called spherical coordinates. Here's a picture of the spherical coordinate sort of diagram. This is also very often referred to as polar coordinates in R3, and I'm quite opposed to this. It's not. It's really very importantly different from polar coordinates. So in polar coordinates, we talk about that distance, r. That is not a spherical coordinate. The way we do spherical coordinates is we describe a point by way of 3 numbers. Step 1, we take that point. Oh man. We look at that plane hinged on the z-axis that contains the point. Right? And with that having been defined, we can write down the following 3 coordinates. Theta, now that is the polar theta, same theta from polar coordinates. But then another angle, the angle called phi. This little symbol here is the lowercase Greek letter phi. Measured from straight up on the z-axis down through this blue plane. All right? And then the distance is not r. The distance is, it's not the distance to the z-axis. It's not the distance from the origin to the projection. It's the distance from the origin to the point itself. And that's rho. And I'm aware that y'all might not have seen some of these symbols before, so let me document. So, of course, y'all know this one is theta. This one is called phi. And this one is rho. Okay, so it's pretty different. Yeah, go ahead.
Just making sure. So the magnitude of rho would be, I guess, kind of like a radius.
Yeah, it's kind of like more of a radius of a sphere instead of a radius of a cylinder. But yeah, totally. Thus the name spherical coordinates instead of cylinder. Yeah, you're totally right. Yep. Right. So this is called spherical coordinates. It is very different from cylindrical coordinates. It's very different from polar coordinates. Please don't refer to it as polar coordinates in R3. It's pretty importantly different. Yep.
Why isn't rho just the same as r?
Well, because r is this distance here. Right? You can see by looking at this triangle. So there's a right triangle right there. Right? R. Let's see here. I guess you could say r squared plus z squared equals rho squared. Right? So so r is measured horizontally as a distance from the origin to the projection instead of from the origin to the point itself.
But it works like r.
I'm sorry?
It works like r.
It works very, very importantly differently from r, because it's different. It's a different distance, right? So we have to distinguish between them for that reason. Yeah. And so here's another thing you can write down. Looking at this angle being phi. Let's see, I need purple. That angle being phi. This angle is phi, right? And you can persuade yourself that r then is rho sine phi by looking at that yellow triangle. Okay. By the way, a couple of bits about notation. I want to recognize. Oh, you had a question, yeah.
Sorry. So, you said rho is the distance of. In this case, rho is always positive.
No, again, so
so
apologies. Yeah, it's another. Again, I was brought up poorly. It's a coordinate, so it can be negative.
So
and negative just means go the other direction.
Like all three of these cases, it can be.
Yep. That's right. None of these, no coordinates that we're talking about here have to be positive. Okay, so a little bit of a notational thing. I want to recognize that it is quite awkward that we're using these two kind of similar looking things to represent importantly different objects in this coordinate system, right? Mathematicians have an unfortunate tendency to use U and V, which look a lot alike, unless you're careful, in the same conversation. And so here's another example, phi and theta. They're very different, but there is a tendency for students to write, maybe their thetas, they get a little bit of tilt on that angle, and maybe the phi gets a little tilt on that angle, and then, which one is that? Let's see, maybe here, more realistically, what if it's like, oh man, I don't know. That you get problematic at some point, right? So please be careful, right? Make sure to be conspicuous in the distinction between theta and phi. Likewise, here's another thing. That symbol is not to be confused with that. The one on the right is P, the English letter P. The one on the left is not P. The one on the left is rho. It's a Greek letter. It's different. It is not the same, and you can't make it the same. It's not sort of you are not welcome to choose as part of your handwriting choices to make your rhos and P's the same. They are different, and if you write a P when it should be a rho, it's wrong. Okay, so you got to be careful with that. I would encourage you, in order to avoid this problem, to spend a little bit of time, I don't know, a couple of minutes, deciding how are you going to make your rows, right? And sit there and just, fill up a page with rows and, get to where it feels pretty good. Make sure that you don't accidentally, it's easy to maybe inadvertently make a lowercase e. Right? So anyway, think it through and just make sure you are able to produce these letters in ways that are distinguishable from other letters. Yeah.
The problem that we had for the homework that was like this,
Yeah.
getting graded, is the grader going to be like retroactively picky about our notation now that we know it? Or
Well, on that exercise, you know, we hadn't covered spherical coordinates at that time,
So
so
it won't be.
it shouldn't. Yeah, I can't imagine. I mean, if you use something along the lines of spherical coordinates, I mean, if you gave different names to these angles, yeah, I'm sure it's fine. Yeah, right. Yeah. So he points to a neat observation, and that is that these angles phi and theta, they're highly reminiscent of longitude and latitude. And they're not exactly the same, but they're kind of close. I mean, theta specifically is east longitude. I mean, if you assume, you know, if you put the prime meridian, you know, the Greenwich line, if you put that on the positive part of the x-axis with, you know, the north pole of the positive part of the z-axis, you know, in sort of the way you would expect, then theta is east longitude. Now, you do have to be a little careful. Phi is not exactly latitude. Let's see here. Let me redraw this blue plane, and then let's see here. Here's our z-axis. Whoops. Our z-axis being like that. And so if this is the Earth, right, then phi is measured like that. North latitude is measured like that. So phi is not the same as latitude, but they're closely related in that they add up to pi over 2. Right? So if you know longitude and latitude, then trivial calculation allows you to compute theta and phi. And once you know theta and phi, you can just convert from spherical coordinates into rectangular coordinates by standard equations that I have written down here. So x is that, y is that, and z is that. Okay, so now I would encourage y'all to memorize these equations. I'm going to give you a great tool for remembering them, and that is to remember we've already made the recognition about r. R is rho sine phi, right? That's just a little, you know, make a little triangle, and basic trig, r is rho sine phi. Well, notice that what that means is that x is r cosine theta, and y is r sine theta, and you've already memorized that. Right? So this is really just plugging in this one fact into the existing polar coordinates equations for x and y. And of course, the other side of that yellow triangle is that z is rho cosine phi, same triangle, right? So really one little trig triangle that we already drew will tell you everything you need to know about these coordinates. Okay, that said, please memorize these. It comes up a lot. Very useful. Okay. All right. Also, not hard to persuade yourself. Rho squared is x squared plus y squared plus z squared. Now, I don't know why it was. I didn't step on the landmine here. Here I had the good presence of mind to not follow that urge to solve for rho, you know. But anyway, whatever. Okay. Right, so suppose you want to convert an equation from one coordinate system to another. So, for example, you know, here's an equation in rectangular coordinates that represents a circle of radius a, centered at the point a comma 0, and that's algebra 2. So I hope you all remember from high school algebra that equation for that circle in the plane. So this circle, how would I describe this circle? What is the equation for this circle in polar coordinates instead of rectangular coordinates? And this is pretty much a matter of plugging in. Literally what I'm going to do is I'm just going to take, well, I have these existing formulas. I know that x is r cosine theta. I'm just going to shove that into there. Let me aim better. Shove that into there. And I know that y is equal to r sine theta. I'm going to shove that into there. and then just kind of, multiply it out. Okay. So it's pretty straightforward. Now, you can also, sometimes you get lucky, and you'll notice here that had I expanded this first and been, heads up, I could have noticed that I have an x squared plus y squared in the equation, and just immediately rewrite that as r squared, because I know x squared plus y squared is r squared. Right? And that would have saved me having to sort of, multiply out the Pythagorean identity here. Right? It's no big deal. It gets you to the same place. But it's a little quicker and slicker to, heads up, if you see an opportunity, if you see an x squared plus y squared about to show up, maybe group those together and rewrite as r squared first before you start plugging in the trig. Okay. All right. So that's all we're going to say about coordinate systems right now. We will come back and do much more with them later. I want to move on now to Chapter 2. We're going to talk about multivariable functions. Again, just very briefly. By the way, it's going to take us a while to get to calculus of multivariable functions. There's a lot to say about multivariable functions, multivariable equations, how to represent geometrically these objects. There's a lot to say. It's not all exactly analogous to single variable functions in algebra. Is the reason that this takes a bunch of time. So there's a tendency for students to think, okay, well, this is just going to be just like single variable, except more variables and therefore more dimensions, but everything else is pretty much the same. It's really not. There's some pretty big differences for various reasons that we'll talk about along the way. So I want to start with talking a little bit about what functions are. Here's an example of a function. Really, a function is a trio. It's not don't think of it as a single thing. Think of it as a trio of three things that are sort of bundled together. It's a set called the domain, a set called the target, and then an expression or instruction or some sort of formula or whatever that allows you to know for any given element of the domain what is the corresponding output value in the target. So here's how those show up here. The domain here is R1. This says I'm defining a function on R1 for any value in R1. For any real number, I'm going to be able to plug into this function. Okay, the target here, R1. That means that when I take an element out of my domain, when I take a real number and plug it into my function, what will come out, I promise, will be in this thing called the target. Namely, what will come out will be a real number. Okay, so we've got a domain, we've got a target, and then we have a formula that tells me how to take, some number from the domain and get the corresponding output in the target. Right, so you give me an x from the domain, a real number x, plug into this formula, and out comes a number in the target, namely an output from this function, which will be a real number, which is therefore in the target. Okay, so it's a trio. So it's all three things. It's not just the formula. The purple thing alone is not the function. It's the formula along with a statement of what are the allowable inputs and a statement, a set representing what are the allowable outputs. Okay. All right. So just while we're here, let me notice that this is a different function. Now you might look and say, well, wait, whoa, hey, come on, it's the same formula. Come on, it's the same function, isn't it? But it's not. Right? These are different functions because here, even though it's the same formula, I have a different domain. This function I have written down here, you are not allowed to put in any numbers other than real numbers between 0 and 1, inclusive. Furthermore, with this function, I have a different target, which means I am promising you more than just that the outputs will be real numbers. I'm promising you the outputs will be real numbers between 0 and 10, inclusive. Okay. All right, so So they're different as functions. Now, why these distinctions are important, we're going to see as we get a little further along. But it's important if you're going to, for example, compose functions. It's important to make sure that what comes out of one function actually is definitely going to be something that's allowed to go into the next function, right? So if the target of the one and the domain of the other don't match up in a problematic way, you can't compose those functions. So we have to be able to talk about the domain and target in order to ensure that we don't write down nonsense. That's one reason. Next, there's issues of invertibility. Now, y'all have all seen in your Calc 1 classes inverse functions. Right? So, for example, when you take the derivative of something like arcsine, well, first you have to write down what is this function, arcsine. And in order to have that function well defined, well, there's lots of issues about, well, wait a second, certain numbers aren't allowed to go in, certain numbers aren't allowed to come out, and you have to worry about what are the domain and target. And if you want to be able to refer to the inverse function, if you want that inverse to be a function to satisfy the rules so that you can actually do business with it, you have to worry about the domain and the target. So anyway, that's part of why. Okay. There is a third set that we need to talk about, and that is the image. The image of a function is the actual output values. And I want to distinguish between the image and the target. They're not the same thing. So for example, let's go back up to this function here. This function here, let's see, let me draw a picture here. There's my inputs, the x-axis. Here's my outputs on the y-axis. The domain, things that go into this function, the entire x-axis, right? The target, the entire y-axis, right? Here's this formula that tells me how to take an x and get a y, right? So there's this separate question of, okay, sure, I've been promised that everything that comes out will be a real number. Does that necessarily mean that every real number will, in fact, at some point come out of this function? Doesn't technically just, who knows? Maybe, not necessarily. Right now, in this case, it does. But in other cases, it need not. So let's look now instead at this function. This function here, and let me do the same deal. Here my domain is the interval from 0 to 1. Let me draw, let's see here. So there's my x-axis, here's my y-axis. I've got this interval from 0 to 1. That is my domain. My target, interval from 0 to 10. This is not to scale. I have this formula. It tells me how to get from one to the other. Let's do it like that. So what actually comes out, though? These actual output values. 3x plus 5, keeping in mind that x is only allowed to be between 0 and 1. Well, everything that's going to come out is going to be between 5 and 8. The actual outputs are just those yellow values. Right? So the target is this blue set from 0 to 10. The image is the actual, what did you actually hit on the target, you might say. You're not necessarily going to fill up the whole target. So the image is this different set. Okay, so we just need to get these bits of terminology out there. By the way, let me warn you about, there's this word called range. I have seen different textbooks that give different interpretations of what this word range means. In some textbooks, they use the term range to mean the same thing as image, which is what I'm doing here. In other textbooks, they use range to mean the same thing as target. Well, they're not the same. this is problematic, right? If you're worried about, hey, is this function invertible? You need to worry about the distinction between the image and the target. And so if someone's using the term range and they're using these terms, using it sort of interchangeably as if it could mean, well, it's either image or target or, who really cares? They're blurring two things that need to be distinguished. So I try to avoid using this word at all anymore. Because it means different things to different people. We have a Tower of Babel situation here. Right? We need to be precise about things, and this term is inherently confusing at this point. So I would encourage you to avoid the term range. If you mean image, just say image. Right? It's unambiguous. If you mean target, say target. Unambiguous. Yeah, you had a question a minute ago?
Yeah, what exactly is the function, well, no pun intended, the purpose of the target as distinguished from the image?
If you want to talk about whether a function's invertible, right, you need to know that if you have a function from A to B, the inverse would be a function from B to A, right? Well, if you want to be able to take a function that goes this way, and if you want to be able to go to the other way, you need to know that for everything over here, in other words, for everything in the target, you would need to know that there's a corresponding what we call preimage. If not every if the outputs don't actually fill up the target, if the range is not equal to the target, which very often is the case, then that's not true, right? And so there would be no value. You need for every point over here, you'd need to be able to say what the corresponding backwards value is. But if nothing hit it in the first place, there's nothing to go back to. Right? So you just can't talk about the inverse of a function unless, among other requirements, the image is equal to the target. So that's one example, right? That's sort of the easiest example to talk about. Yeah.
Can the image extend outside the target?
No, it can't, because that's the rule. When you're defining a function, when you say here's the target, it is on you as the function definer to make sure that every output value is in the target. Right? That's the purpose, the function of the of the target is to be the thing that definitely contains all of the output values. Yeah.
And is that how calculators can find the minima of functions, where you bracket it between where there's only one local minima inside the bracket? So you set a target within that?
I mean, this is a pretty abstract thing. I mean, how calculators do that, probably different things in different instances. I don't think so. We can talk about it after class if you want. Yeah.
What's the point of the target if the real thing we're interested in?
Yeah, no, that's a great question. So let me see if this is where you're going with this question. Why should I ever talk about a target that's bigger than it needs to be? Right? Why wouldn't I just throw away target and just always use image? Right? And in an ideal world, yes. But in reality, I don't want to have to create for myself a math problem every time I just want to define a function, right? So, for example, maybe I want to talk about, f of x equals 3x plus 5, and I'm going to be let's make it harder. Let's make it f of x equals, x to the 7th minus x to the 8th plus x cubed. Right? Nasty little function there. And look, why do I need this function? Well, because I'm going to be plugging in values between 0 and 1 into this function. And well, what's going to come out? Well, real numbers are going to come out. Now, why am I interested in this function? Maybe I need to talk about derivatives of this function. Maybe this represents something I need to study, and differentiation or something like that is relevant, right? And I might be able to do everything that I actually care about just from having written this down, right? And I don't want to have to, every single time I write down a function, worry about, oh, wait a second, this clearly does not fill up all of R. So I've got to do an optimization problem and figure out where's the biggest value, where's the smallest value, what is the actual image can be really hard to find sometimes, right? And so it's very convenient just to say, look, this is what I'm doing to these numbers between 0 and 1. And, look, real numbers come out. have any particular need at this moment to refine exactly which real numbers come out. Yeah.
But why isn't the target then all numbers?
Well, it just isn't. I mean, look at this. I mean, if you plug in values between 0 and 1 into this function, you won't get all real numbers.
Then why would you define it as something else? Why isn't it always all real numbers? Why would you define it as 0 to 10 sometimes?
Right, because sometimes I do want to be able to invert the function. So it's very convenient for me to be able to write this down if all I need to do is take a derivative or something, right? Okay. But if I want to talk about the inverse, I cannot talk about the inverse of this function, because this function, as written, is not invertible, because I do not fill up the entire target. Right. Yeah, no, that's good questions. Yeah. Okay. All right, so that's just a little bit of terminology. With that under our belts, here's what a multivariable function is. It's no big deal, really. It's just a function that instead of having a single real number go in, we have several multiple, you might say, variables go in, right? So that's the name, multivariable. And by the way, you might have multiple variables coming out, too. Notice that there's two different outputs here. X plus y is the first output, and then comma, and then 3xz minus yz is a second formula. So there's two output variables here. 3 input variables, 2 output variables. Yep. Okay, so multivariable functions. Now here's a convenience of notation, and that is, let's think about these 3 variables that go in. I could think of this as 3 real numbers, and I suppose that's fine, right? But let's think now momentarily a trio of real numbers. What's an alternative way to think of a trio of real numbers? I can think of a trio of real numbers as a point or a vector in R3. Right, so instead of thinking of it as 3 numbers going in, let's think of it as a single point going in. So it's just a different way of thinking about it, but you can think of this function as being a function where 3-dimensional points go in and 2-dimensional points come out. All right. Alrighty. Now, there's a bunch of examples that I have in here. I'm just going to show you one because we're behind schedule as usual. And this is what I like to call the temperature function, which is pretty relatable. Right? Temperature, something we can all kind of get accustomed to. So let's suppose that we were in a rectangular room, which we kind of are, pretty much, except for a couple of weird shapes here and there. And we can measure our coordinates x, y, and z from some corner. I don't know, let's say this corner of the room down here. Let's call that the x-axis, and that's the y-axis, and that's the z-axis. Right? So x, y, z. So any point in space, like this point right there, let's imagine some point right there. I can describe that point by 3 numbers, x, y, and z, the coordinates of that point. I can then say, here's the formula for my function. If you give me an x, a y, and a z, I'm going to go to that point in space. I'm going to put a thermometer right there, and I'm going to measure what's the temperature of the air at that point. Right? So if you give me an x, a y, and a z, I give you a T, temperature. So what we have here then is a function that's it's tempting to call this from R3 to R1, but just remember that the domain is a subset of R3. We do have to stay in the room. You can't let x be 1,000,000 because that's way over there somewhere. It's outside of the room, right? But inside of this room, 3 coordinates describing locations in D are the input, and a real number, that being the temperature at that point, is the output. So that's a multivariable function. Yeah? Everybody good? Okay. All right, various other examples. I'm going to let you guys read them. You can think about altitude as a function of longitude and latitude. You can think of location as a function of time. If you're taking a road trip, right, driving around, you give me a time, I can tell you x, comma, y, longitude, latitude, where was I at that time. Okay. And here's a wacky example. Let's call this the weather function. If you give me a location, I can give you a bunch of variables representing the weather at that point. Right? At, certain longitude, certain latitude, we can talk about, well, what is the temperature and the barometric pressure and the humidity and the wind speed. And that's a short list of weather variables that we could be interested in talking about, right? So the reason I like this example is this shows that multivariable functions are not sort of some abstract mathematical construction that happens in some ivory tower somewhere that has nothing to do with the real world. We're just talking about the weather, right? And we've got a multivariable function with 6 variables. So extremely relevant, extremely natural, and ubiquitous. Okay. All right. Quick observation. Y'all have all seen these kinds of pictures before. This is called a graph. This is a graph of a single variable function. Y'all have seen this in Calc 1 classes. Graphs are awesome. I want to lead with that. Right? Graphs are fantastic. It gives you a picture, a way of understanding what you would otherwise only write down algebraically. This is some sort of, maybe that's a cubic polynomial of some sort, right? So that's super. It's so super that in single variable calculus classes, this is almost the only way that you ever even represent functions. It's that good. Right? You don't need any other way to represent functions, single variable functions. So, I'm a big fan of graphs. Okay. And now begins a 6-week-long kind of tirade against graphs. I just want to be on record that yes, I know they're great. I understand that. So here's the problem. The problem is that you guys are graph addicts. Right? You guys... all exceptions granted, might be under the mistaken impression that whenever there is a picture, that picture is necessarily a graph, and it's not. Right? Graphs are useful in certain contexts. Graphs have certain features, like in a single variable context. The geometric feature of that tangent line being sloped the way it is a geometric giveaway of an algebraic fact about, the derivative, the algebraic derivative of this function, an algebraic property that it has of being negative. Right? So, yeah, it is really useful in a lot of ways, but we're going to find in this class that there are severe shortcomings of the graph construction that cannot be fixed. And I'll talk about them as we go along. And we need other different ways of representing functions, other kinds of pictures that are very importantly not graphs. And you might say, by the way, that what we have here, this is the geometry of the derivative. We have a geometric interpretation here of a certain aspect of calculus. Derivative is interpreted in the graph as a slope. So the geometry of the calculus in a graph context is not the same as the geometry of the calculus in other contexts and other kinds of pictures that we're going to draw. Right? So this is a big deal. You've got to make a distinction in your mind going forward. Whenever you see a picture, you have to ask yourself, wait a minute, whoa, hey, slow down. What am I looking at here? Is this a graph? Is this a level set? What am I looking at? And then whatever calculus you're dealing with, you have to ask yourself, okay, in this context, what does the calculus look like? And if you make a graph interpretation in a level set context, you're writing down garbage. So anyway, heads up about that. I like to make a big deal early on about be ultra prepared that we're not going to rely exclusively on graphs, and try to start pulling yourself away from the sort of instinctive knee-jerk reaction that pictures and graphs are kind of interchangeable. Okay. So here, by the way, here's a different way we could represent a function. Here's a function that we talked about from R3, 3 input variables. to R2, two output variables. And I could say, well, for this value of x, here's the corresponding value f of x. So the point, x goes in, this point, f of x comes out. Three-dimensional point in, two-dimensional point out. There's a picture of this happening. How would I draw the graph of this? Not clear what that would mean, right? And I'm going to say more about that a little bit later on. But very importantly, this is not a graph. And also very importantly, it is not clear how we would draw a graph of a function of this sort. All right. By the way, it also turns out that this is a really important kind of a picture to make sense of. And if you think about it, this is really kind of honest. It's honest in the sense that, well, we do have this set called the domain, where inputs come from. We have this separate world called the target, where outputs land in. We're drawing them separate. They are separate. That's really kind of more fundamentally what a function really is. It's a picture kind of like this, yeah.
Would you define them using the same coordinate system or like different coordinates?
Oh, well, here I'm representing the points in the domain with rectangular coordinates and points in the target with rectangular coordinates. Yeah, I mean, let's not deal with that at the moment. Yeah, right. Yeah. Whereas, let's look at a graph. There's something really kind of weird about a graph if you think about it. Inputs are there, outputs are here. We have a single variable function, and yet we're drawing a two-dimensional picture. What is this space? This R2. It's not the domain. It's not the target. This is like a Frankenstein space where we took the domain and the target and we kind of spliced them together and we made this new monster of a space in which we drew the graph, right? But it's our own little creation, which again is great and it has its purposes, right? But it's a little unnatural and contrived. Okay. All right, I've complained enough. Okay, moving along. Let's talk about equations. Here's an example of an equation of two variables. And y'all have seen equations of two variables. Here's another one. Equation of two variables. We can talk about a solution. What do we mean by a solution to an equation of two variables? Well, we mean a pair of values that when you plug in makes the equation work. Right? So x equals 1, y equals 1 is a solution. That pair is a solution to that equation. You might say that point satisfies that equation. And so this is not a hard thing to think about. Y'all have done stuff like this before. Right? This is an equation on two variables. So here's R2. Let's call that the x-axis. Let's call that the y-axis. And that equation, I'm going to say, describes a line like that. And what I mean by describes is if a pair of numbers x and y satisfies that equation, that means the point is on the line. Right? And if, on the other hand, if you come up with an x and a y that don't satisfy the equation, that is a point that is not on the line. Right, so that's what we mean by saying that this is the equation of that line. But just grammatically, another way to say that would be that the line is the set of solutions to the equation. That's just semantics. Is everybody on board with the okay? Nothing too creepy here. All right, so here's where we're going to stretch things a little bit, and that is, what's the set of solutions to that equation? Z equals x squared plus y squared. Okay, let's count them up. X, y, z. We have three variables now, right? Yeah, you don't cover this kind of stuff in a Calc 2 class or in an Algebra 2 class typically, right? So, what is this equation, and what would it mean to talk about a solution to this equation? Well, it's totally analogous. Now, instead of two variables, now there's three variables. So we're going to look at points on a three-dimensional axis system, right? X, Y, Z. And this equation is going to represent some sort of a surface that I don't want to presume I know just yet. But some sort of a surface. Some sort of a bent, maybe curved, who knows, we'll work it out in a moment, surface. And same deal, if you have a point, if you have a x, y, and z coordinates that satisfies that equation, what that means is you have a point that's on the surface. And if you have some trio x, y, z that does not satisfy the equation, then that means you're talking about a point that's not on the surface. Yeah? Everybody cool? So what we want to talk about then is, given an equation, how do we figure out what that surface looks like? What is the surface that is the solution set of this equation? Or this equation is the equation of what? Okay, so there's some algebraic mechanics here that we have to worry about, and roughly speaking, we're going to find different ways to take this harder problem than we've seen before and to reduce it to an easier problem. Mathematicians love this. If you have a hard problem, step 1, reduce it to an easier problem. Step 2, solve the easier problem. Right, the classic method in math. Okay, so we're going to take this equation of 3 variables and try to figure out different ways, for example, to turn, let's relate this to, can I find a way to think about this as relating to an equation of 2 variables, because I'm real good at algebra 2, right? I know if you give me an equation of 2 variables, I figure like I got a good shot, you know. Okay. So here's the idea. Let's take this equation and let's say, okay, what if I require a point not only to satisfy that equation, but I furthermore require that the y-coordinate be some number c. Now, am I allowed to do this? Yeah, it's free country. I can do whatever I want to do, right? Yeah. So, okay, but I have to confess, if I do this, if I insist that y equals c, I have to recognize, well, that means I'm not going to get the whole surface. It's entirely possible that some points on the surface will not have y-coordinates equal to c. So if I insist that y equals c and points beyond the surface, I'm only going to get some of the points on this surface. Which points will I get? Well, this is some sort of a surface that I'm trying to figure out, and this is a plane. And if I insist that both of these equations be true, I'm going to get the collection of points that are on both the surface and the plane. Namely, I'm going to get the intersection of the surface and the plane. And sometimes this is called the cross section. So we got this surface here, I'm trying to understand. And insisting that y equals c means we're going to look at this plane where y equals c, and we're going to look at, imagine a knife coming down and slicing that surface, and we're looking at that slice. Does that make sense to everybody? Okay. All right. So having done that, well, now the algebra is pretty straightforward. I mean, if y is equal to c, let's plug that into there, and then this equation becomes that equation, and that is an equation I understand. There's only 2 variables in that equation. Z is equal to x squared plus a constant that I can write down. C is a constant. Well, that's algebra 2. Right? It's a problem. By the way, I hope everybody remembers your algebra 2. It's definitely going to come up a lot in this section. What most students have trouble remembering is which way do hyperbolas go. Right, so you want to brush that up. I'll talk about that in a little while, either in a few minutes or on Monday, time depending. But anyway, make sure you're good with all your algebra 2 because it's not going away. So that's a problem. So what this says is this surface If you take a cross-section in the plane y equals c, you get this parabola. So the surface has a cross-section that's a parabola. Specifically, I know where to draw this parabola. It's in the plane y equals c. And what to draw is, well, this is a parabola that's pointing upward because of the positive sign, upward in the z direction, and it's been shifted upward by an amount c squared. Algebra 2. So that gives us a picture that looks like this. So in this plane, where, okay, let's see if I can draw this now. In this plane, right, there's a plane where y is equal to c. Let me do this with where y is equal to c. It's been shifted up by an amount c squared. Parabola. Yep.
Now, will all the possible c's be used to generate this process?
Again, free country, you can do whatever you want. I would encourage you to think about, because you're trying to understand this surface, right? And the more c's that you think about, you don't have to enumerate infinitely many, right? But the more c's that you think, well, what would happen if c is this or that, then the more cross-sections you'll have to look at, and the more sort of information you'll have to assemble the surface that you're interested in.
But if the surface is constrained, obviously, like dimensionally, is there a point where
I'm not entirely sure what you're asking. I think you're asking about a hypothetical scenario, but I don't know what the hypothetical scenario is. So maybe if you can come up with an example of, let's talk after class.
Right, sure.
Yeah, cool. Okay, so for this value of c here, we get this parabola shifted up by that amount. Now I'll observe that for a different value of c, well, we're going to get a different parabola shifted up by a different amount because, well, if c is different, then c squared is different. Right? The smaller c is, the smaller c squared is. So the amount that these parabolas are shifted up, that amount is itself kind of parabolic in a way. C squared, right? So you put this all together, and that suggests this kind of a picture. Now, you got to use your own geometric imagination. What do you do with this? What do you do with this collection of parabolas that are kind of, in planes perpendicular to the y-axis and shifted up by different amounts depending on where they are? Wow, you got to, what do these create when you put them together? It's a bit of a challenging geometric visualization problem, and it's also a non-trivial art problem, right? So I encourage everybody here to start thinking in terms of how you can get good at drawing things. And by the way, I always offer every semester, come to my office hours, and I will show you the tricks that I know for how to draw geometric figures well enough, right? Because there are things to know, and if you're not good at, some students will come to me and say, well, I'm just not good at drawing. What should I do? And I say, you should get good at drawing, because this is an unavoidably geometric class. It just is. So this is something everybody can work on, everybody can improve on, and we need to actually do that. Okay, now, why did I set y equal to c? Why didn't I set x equal to c? Well, let's do that too. You can set x equal to c, plug that in, you get these parabolas. Now these are also upward oriented. These are upward oriented, but in planes perpendicular to the x-axis, which look kind of like that. And again, hard to draw, but you try to imagine, okay, like for example, that one maybe is in that plane perpendicular to the x-axis. And if you push that plane back, the parabolas are going to dip down lower and then come back up for the same reasons. Okay. Or we could set z equal to a constant. That gives us this equation. And so in horizontal cross sections, we have circles. Again, algebra 2. Make sure to remember your algebra 2. Right? Circles, where the radius is kind of the square root of the height c, where you're making your cross section. So you're going to get a bunch of circular cross sections like this. So now use your geometric imagination. What happens when you take, what shape has these cross sections perpendicular to the y-axis, these perpendicular to the x-axis, these perpendicular to the z-axis? How about a bowl? Right? Does that seem kind of plausible? You just have to take these pictures that we've drawn and kind of assemble them in your mind. And what do they sort of assemble into? And this is called a paraboloid, by the way. Where's the Where did I write this down? Here we go. Paraboloid. Okay, so this is our first tool for understanding equations of three variables. There's several others that we'll talk about on Monday because we're out of time. Y'all have a great weekend. I owe y'all an email as to what the homework is. Let's see. Let me think it through now. We just finished lines and planes, coordinate systems, functions. We have not finished 2.2 on equations. So anyway, so those three sections will be the ones assigned, then I'll note it in an email. See y'all later. Oh yeah,